marker. So where are we now? This termination of beta. Yeah, we did this one, right? This one already. So we go. Okay. We have already determined one multiplier, which is already has gone. But so we want to determine another multiplier. So then we have the
pointer.
Oh, yeah. Okay. So in order to do that, we first define actually thermodynamic quantity out of the microscopic expression due to the statistical mechanics. Okay. So this is the microscopic expression due to the statistical mechanics. So this is the weight factor, probability factor of the probability of J state appearance, energy of J state appearance, right? And we take the average of EJ, this energy, over all the state. Yeah. Okay. This is this is the average of EJ energy of entire state. Okay. Then it is average. So this is assumption. We assume that this energy, average energy, is actually observable, equivalent to observable of some thermodynamic energy. Okay, I think this is a very reasonable assumption. And also average pressure. Pressure. This is the pressure of J state. Okay, and we take also average over this J state pressure. Okay, then this is average, and but this I mean J state. What is the expression of pressure in terms of EJ? Because we didn't have any expression for pressure. So actually, this is the expression of pressure. Why? You know, when you have a box, you apply pressure, right? Then volume changes. That is a volume work done to the system due to this pressure, right? So this pressure is actually Pj times dV is an energy change due to this pressure. Okay, this is a work. So this is the expression of pressure. Ej or derivative of Ej with respect to V is the expression of pressure. Okay. Actually, if you change the temperature, okay, if you change the temperature, population of J changes, not the Ej itself. But when you apply the pressure, then Ej changes, Ej itself changes. Okay, so we put this expression into here this is the problem which we expected. How do I manage this one? Anyway, maybe I will write. This is in the border, so also easy to see because E minus EJ over EV, number of particles fixed, exponential minus delta EJ. Okay. So now we have two thermodynamic quantities, average E and P, which can be compared with the thermodynamic quantity itself. Yeah. So then actually this I will go over all the way and come back. This is the equation which we have to derive, but here I put anyway. You know, this d over dv average we have to take average of this dE, average of energy over V, then it becomes this equation: average P pressure plus E times P, average of E times P, and average of E times average of P. This can be you can derive this one from those expressions. You know, take this derivative over V and change. I mean, take the derivative. It's a little bit complicated process, but you can do it. It's a very straightforward algebra you have to do, and this one also. You have to take the derivative of P over V, and you get this equation. So it's all average, you know, quantity. And so from those two forms, we sum up those derivatives, and then you get this equation. Okay, and there's some thermodynamic relation here. This is a thermodynamic relation which can be thermodynamically derived. Okay, and you compare those equations. This is average, microscopic average of microscopic quantity. But because it is average, you can compare with the energy, with the thermodynamic energy. This one also average of microscopic pressure, which can be compared with thermodynamics and so forth. Okay. Then you can, if you compare those two equations, yeah, in the wait, what is here? Something wrong here. Oh, because I copy and pasted this one. Actually, here this should be, I believe, in the thermodynamic. Where's my note? Laptop? No, sorry. Laptop is wrong. Because I didn't have the time to put it all in the equation in the computer, so I have some leftover. Yeah. I would like to break the equation downstairs. This should be dE over dt. This is thermodynamic dV equation. plus okay. This is equation which can be purely can be derived purely thermodynamic manner. Okay, so you can compare these two equations, assuming equation not this one, but this one and that one. This equation and this equation. Okay, then you find beta equal constant times t. Sorry. Constant times 1 over t. And this constant can be 1 over t. So this constant can be k, Boltzmann constant. This way, you find that beta is related to 1 over kt. So now our distribution is t say not say fj equal sum over exponential minus bj over kt exponential minus ej over kt. So this is the Boltzmann distribution. So, but now we have to derive these two equations, right? So I do it now on the blackboard, the whiteboard. Okay, so first we take a I can write here. Take derivative of this should be this derivative of e then delta fixed. This is average energy. Derivative of average energy, microscopic energy over volume. So this is 1 over dV. J. In this case, we don't know what it is yet, right? So we just leave it beta over EJ. Exponential minus beta EJ. So first, this one should be, in this case, we have to take beta EJ here, right? And minus first class VE over dV exponential beta EJ plus J times minus beta beta EJ over dV times exponential minus beta EJ. And now this EJ exponential minus beta EJ this one here the sum minus beta TEJ over dV exponential minus beta EJ. Okay. Okay. So and we can just single out. This is the I'm missing, yeah, I'm missing something. Here, I'm missing something here. Yeah, this should be part of exponential beta EJ multiplied to here. Okay. So then from this part, first J exponential minus beta EJ. This one factor disappears, canceling with this, and minus J EJ over dV. Maybe I should put minus here. Exponential minus beta EJ. Okay, this is the first term. My note, this minus is missing. That should be minus. Oh, but why I put the minus? 2j. and plus this part is done, and this part is now minus beta beta sum exponential minus beta ej square, this one, and sum sj ej over dv exponential minus beta ej. Again, due to this one disappears. Minus beta, yeah, minus beta. Distributed. Yes. And this one is deriving this by e. And there must be ej. Because this ej should be multiplied. And the derivative is taken this one and exponential. So okay. So then plus beta dj exponential beta ej and minus beta ej. This is j. Sorry, beta ej, dej over dv exponential beta ej. Okay, and this in this case, this one is inside of j. So this thing. This sum is where? Sum is ej exponential dvj exponential beta j. And okay, ej technically multiply this one and now this one summation minus beta ej minus beta ej and then ej dv and this should be this and this should disappear is this one. So ej exponential ej. This one comes, but then comes into here. Again, derivative of this, multiply this one. And taking the derivative of this one, and then it will, this one will appear, taking derivative of this one, dj over dv, and explanation from here, and then this one should multiply delta. This is okay. Why? Yeah, EVA. I'm going to maybe too fast. So k exponential minus delta EJ square and sum J dEJ over dV exponential minus delta EJ and this one plus EJ times this one times minus delta dEJ over dV exponential minus delta EJ and all over this one should be inside of the summation. Is that correct? Yeah? Yeah. Okay. And this part is minus exponential minus delta EJ square minus square, and I have to take the derivative of this. And first we have to multiply J EJ exponential minus delta EJ multiply the derivative of this minus delta EJ over dV exponential minus delta EJ. I think this is the same, right? Yeah. Yeah, this is the same. Okay, so then, okay. And from here, I think we have to get one. According to my note, this should be some exponential minus delta EJ some dEJ over dV exponential minus delta EJ. This comes out. How? This one. Oh no. Yeah, this. Why? Something wrong here. Derivative taken this one.
Del E over del V e to the power minus delta EJ.
Which one?
The final expression.
Can you write down?
Del E.
Find out. There's certainly there's some mistake. Yeah. This factor this factor should come out. Can you write here? Somewhere. Yeah.
Should I
bu-
delete
blue,
the-
blue.
I cannot insert here. I can write face.
Okay, sure. Yeah, you can delete. Oh, everything? Oh, I made a mistake in the very beginning.
I'm not able to grasp that.
Yeah. Great. But there must be a square here.
This is the original expression I have not done anything. Now I'm doing it.
Oh, okay. Okay. You're the derivative. Yeah.
This is the denominator part, and this is the differential of the numerator part. Denominator d by dx of numerator minus dt d by dx on denominator whole
So
square.
you just got
So this is the denominator part, and this is the d by dx of numerator part minus of.
I see. I forgot to mark this one. Okay. That's why. Yeah.
Should I do the later one or should I?
Yeah, I forgot the. Yeah, that's why it disappeared. Yeah. Okay.
I can multiply with summation of del beta upon del beta into exponential of beta times beta plus the second term. So this will be like minus. So we have minus beta here. So this will be minus of summation of exponential of minus beta times beta, and then summation over ej exponential of minus beta times ej.
They cannot see.
Del ej upon del beta.
Okay.
Minus this term summation of ej exponential of minus beta times ej. And this is minus. This will be plus.
Okay. Yeah.
Summation of minus beta times ej into beta. We have multiplied the beta also into del ej upon del beta. So, and the denominator will remain as it is. I'm not writing the denominator. So, if we can look at this expression.
This one goes out.
Yes.
Yeah.
This one goes out. So the final expression would be beta times Ej, which one will go out? Exponential of minus beta is
Final expression I have written here.
this one and this one, and this one will go out. Yes. So these two will go out.
Okay.
Mm-hmm.
Okay, so I will write the final expression.
Sure.
It's a kind of very messy derivative. So you just try yourself. Everybody. This is a home assignment. So I will doing this way. You can derive finally. But the problem what I have was I forgot to multiply this one. That's why I took trouble. Okay. The final expression, I mean, in this the summation thing is the sum exponential minus beta ej. I think you figure out how I'm deriving this equation, right? Although we are not successful, exponential minus beta ej, okay, plus minus beta ej times beta ej, not beta, derivative ej over b exponential minus beta ej. Okay, and over exponential minus beta ej. Okay, and minus beta ej sum ej exponential minus beta ej times okay minus beta sum dej over dv exponential minus beta ej. So taking those derivatives carefully, you get this expression. Okay? And then, you can figure out this one. This one was minus, I think, p. Minus p. So from this part, this is a minus p. Average, take this minus p over this, this weighting factor. So this is minus p, right? Average of this one corresponds to average pressure. Okay, and this one is minus beta. This is the E, average of E, and this is the average of P. But also again, there must be minus P, so this should be plus. Okay, taking this two factors, multiply together over this distribution. Okay. Over this distribution. But this one again, has a negative sign. So this negative sign disappears. And average. And this one is minus average of E, right? This is average of E by definition. And here there is negative minus the plus. And here it is also average of P. Okay. So this is the expression which I just have shown on the screen. Yeah. Oh, this one is minus, negative, so there must be some problem here. Minus, minus, and this one should be minus, so it should be minus. Okay. This is a minus p, okay? And minus beta, and here there is another minus. There it is. Okay, doing same manner. Because I don't have enough time, so doing same manner, you can get for. Did you write this one already? Yeah. So I will just delete. So this is a home assignment. You can take it yourself. House. Your dormitory. So deep. This is not strong enough. Beta. And D is also becomes very messy expression, which is some exponential minus beta EJ square sum J minus BEJ over BP, B beta no. Two. What are you going to do? Oh, yes. So it says B over EJ minus beta EJ times beta J minus the initial plus beta EJ square sum J minus EJ over EB exponential minus beta EJ sum minus EJ exponential minus beta EJ. Here's the note here. Even in my note, derivative of beta oh, I see. Okay. Yeah, this is okay. So actually, this DEJ appears for because PJ was DEJ over DB, right? So actually taking the derivative of P, this is the expression of P, and take the derivative of this average. You have to first you take the derivative of this factor over beta with respect to beta. It comes, so then EJ minus EJ comes out. Okay, and you have to multiply this factor to here, and next is the degenerator. I mean this one downstairs. So this is the expression, and so here, no, this one says, okay, exponential minus beta EJ over this one is minus negative, so EJ times PJ, this is PJ times EJ exponential minus beta EJ, right? This one is the PJ expression of PJ minus this one can be split into two factors. Exponential minus beta EJ J. This is again minus P J plus PJ exponential minus beta EJ. Splitting this factor into two, exponential minus beta EJ sum minus EJ exponential minus beta EJ. So this one is again PE, right? P times E, average of P times E, pressure times energy, minus this is average of P times average of E, but there is some negative sign, so this should be plus. Minus. Is that correct? Yeah, this is the correct expression. So also please, I think you can derive it. This is not so difficult. I don't know why I put here E, but this can be also P from the beginning. Maybe my expression was so I derived the equation. These two equations now, so you can get this factor, right? So now we established the correspondence between microscopic quantity with the macroscopic thermodynamic quantity. Yeah. And please try by yourself. And this will be very, kind of the good training for, the lecture from now on. We do similar calculation, lots of similar calculation, much more complicated. Okay. So any question so far? Okay. If there's no question, I will further a little bit. Because there are there isn't much time, so I go with the using the slide also. So now we have established some thermodynamic correspondence between mechanical quantity with the thermodynamic quantity by taking average, statistical ensemble average, right? So, but what we want to know is to find is actually this expression. This is the expression which is most famous, most important expression, which relate microscopic. By the way, I think I didn't define Q, but Q is just this. This is called partition function. Or state sum sometimes. This is called state sum or partition function. So actually, this expression says the partition function defined here is related to, has a very simple relation with Helmholtz free energy. This is Helmholtz free energy, okay? Related with the just logarithm. This is the most important expression. So the purpose of here is how to find this expression. So this can be also found by doing similar analysis and comparing the thermodynamics one. So we first define log Q by just a simplification of notation, right? Log Q equal R. This is the definition, okay? Or here, what I wrote here? This L is should be dot dot dot. I think some code changes. Okay, so it's a number of E, J state E, energy of the state. Okay, and this should go to all the way, many. And R is a function. This is saying that R is a function of beta and many E's, different energy. Okay. So and this Q log Q, then log Q should be this, right? Defining this and this. Okay. And if you take the derivative of R, this is simple total derivative, right? Of course, you have many E's, so you have to take sum of derivative with respect to each energy, energy of each state, okay, and sum up. Okay, then and take the derivative, actual derivative of this expression, then you can get this expression, right? R over beta. Or if you take the derivative of beta, then this is a logarithm. Derivative of this function makes this one comes into the this I don't know, the generator or something. Generator downstairs, and also this one, take the derivative of this one, create this function factor. So this is nothing but the average energy, energy or average energy over energy averaged over the state, many states. Okay, and also take this derivative. This is also not very difficult. Just if you take the derivative of logarithm, this one comes downstairs, and if the beta comes out and exponential stays here. So this is this is actually probability of finding energy in K state, right? So I mean the system in K state. So this is a beta minus beta Fk, and putting those expressions. So this is average energy. This is a average of no. What is it? Cannot see. Beta. You can see. No. Wait. So minus beta Fk dr equal, this is average E, and this one is minus beta Fk. Beta Fk. So yeah, this here. This is very awkward here. But why just appear in this? Yes. So what is written here is the delta dr equals minus E d beta minus beta j fj ej, because the expression of dr is expression of dr is here. We put this expression to here, and this expression to here. So actually, this is a probability distribution. So it is we put this one here and close this. Okay. Then it becomes R plus beta E equals beta VE minus FJ VEJ. Because there's a expression, I mean, VE can be E V beta plus beta CE. So putting this one into here, then you get this expression. So question is, what does this mean? Actually, this is what we have done already. You know, remember, again, oh, wait. I'm explaining here again the meaning of yeah. Meaning of FJ, meaning of this term. Actually, this term is kind of the average work done by pressure onto the system. You know, this one. You know, I told you that. Yeah. You know, taking the derivative due to pressure. Change. Yeah. Yeah, changing the volume, then you know it will do a volume work, right? So you know, changing by applying the pressure, changing the volume will change the energy. So this change of energy due to volume change is a volume work, statistical. I mean, work created by pressure, energy introduced by pressure. So this average of this energy should be work, some thermodynamic work. So if you look at, you know, this is the average energy, and this is the average thermodynamic work. So then, by first principle of thermodynamic, first principle of thermodynamics, this one should be sum of this one and this one, right? This is the actually, if you subtract work from total energy, the rest should be the heat, because sometimes definition. Okay. If you have a system, okay, system can, into the system, heat can go on out, and for open system, and also by pressure, this volume, if you volume will change, then this work should be, if you put pressure here, then this work is, I mean, the energy due to the work is introduced in this system. Also, heat is going out and in. So entire energy change can be written by dQ minus plus dw. Okay, this is the first principle of thermodynamics. Or it's simply this is the energy conservation of the system. Okay, energy of the system can be changed, either change of heat or change of work. And this work is created by changing the energy state of energy of the state. Okay, so that's why it can be this. This one is this. The delta Q is this. This is like heat. Sum of this and this should be this. Okay. Then from this equation you can get this expression. Okay, because beta is a 1 over kT. Okay, and this T dq reversible over T is ds, change of entropy. Okay, so you get from this you get this expression. Okay, this is a log Q, and taking the integration of this equation, you get this one in the left hand side and S in the right hand side. So S should be 1 over actually just taking the making the algebra, you get this equation with some unknown constant. Okay, so this constant can be 0 or whatever any. This is a standard state problem. So constant can be 0 according to the Nernst hypothesis. Okay. So, and another messy equation appeared.
We can teach another 5 minutes.
Okay, I will roll up. Anyway. So actually, what I'm doing with here is what was before. What was before was SKT. You can prove this expression. This expression, taking the derivative of logarithm Q over T with respect to T, then you get this expression. This is a similar manipulation which we have done before, and get this one. So this we can get this expression by taking this derivative, and also for P you can get this expression. Both are related to log Q, partition function, derivative of partition function. Then, and entropy was before we derived, entropy was this. So entropy is this, and putting all together, or you can see here, E minus Ts, this E minus Ts is equal E is kT square over this times this derivative minus T minus T times entropy expression, right? And if you do just a simple manipulation here, actually this one just disappears, and minus T times K comes to here. This you cannot see, but this is log Q. Okay, this proves the first Yeah, this one. Okay, so all of those messy derivatives, after taking derivatives, you get finally with this expression. Okay, this is the way to establish. There are many ways to establish a quantum microscopic state, average of microscopic state with two thermodynamic state. But this is one very popular way of finding the relation between those two different worlds. Okay? And this is again the Homer same. Okay. Maybe you cannot write all the way, so you have to derive those equations yourself. Not very difficult, right? Just take time, little time. Okay, any question? So we now establish the relation between microscopic quantity and thermodynamic quantity. And we will use this type of quantity all the way to discuss about the liquid state. There any question? There any question which is kind of what do you call very principle thing, not the derivation, but more physics. Derivation you can do it by yourself, so no problem. But if you have a question about the concept, you have to ask now. Yep.
While considering the average pressure.
Average what?
Average pressure in this.
Average pressure, yes. Why? Huh? What is the question?
Why the average pressure is different from thermodynamic pressure? We can calculate pressure with energy derivative.
Yes, energy derivative with respect to V, volume.
We constant with respect to volume, but we are taking the average to increase the.
Yeah, actually, you can calculate the pressure for each state J. Okay, but that is a fluctuating state. You have to take average to get observable pressure. That is what I have done. It is very important, important question actually. You see, there is another way of explaining. This is also conceptual one, so I will explain. So you have many states, right? 1, 2, J is 1, 2, and some J. So yeah, the particles are fluctuating with respect to due to the thermal motion, right? So EJ is also fluctuating. So if you take the derivative of EJ over V, this quantity is also fluctuating. Yeah. So you have to take the average over this J. Then you get the average. Yeah. So this is the pressure for this J state, some J state, but this is fluctuating. So you have to take the average. And there is another simple idea to relate this derivative of energy with pressure, volume to pressure is actually quantum chemistry. Okay, you know, I think in the bachelor's course of physics or chemistry, whatever, you learn particle in the box. Yeah, quantum chemistry, particle in the box. So if you solve particle in the box for this Schrödinger equation, you get the energy, which is something like I don't know. There must be some H or something like that. This is a quantum number, discrete quantum number. Yeah. Here, this is L is a size of box. Okay. So if you change size of the box, this EJ change. Yeah. That is one way to understand this problem. So EJ change means if you make the pressure, if you add the pressure to change this L, then EJ change, which is you know, the energy is introduced by this pressure into the box, changing the box size. If you change the box size, you know, energy changes. The state of energy changes. This is a very simple, explanation also. Other question? Especially conceptual questions, very welcome. Not the derivative, derivation. Derivation is very awkward. So now you understand what the statistical mechanics is. Yeah. Okay, so class dismissed today. Okay, so see you tomorrow.